are in Africa, in countries with low per capita incomes. They raise eyebrows at seeing together the word nano, which the idea is that it's something expensive. Everything that deals with nanotechnology must be expensive. And the word malaria. These two things do not seem to go well together. And in part, probably, this is because some of our popular science journals that maybe have depicted nanotechnology as something, as in the two images on the left, which is very sophisticated, little machines that obviously they must be expensive if they are like that. We know that nanotechnology is not that. We know that when we talk of nanotechnology or nanomedicine, we are still in the field of macromolecules, macromolecular components that maybe the combination of 2 or 3 of them provide a new function for this nanostructure. This is what today is nanotechnology. And obviously, as I will try to communicate today, it's not that expensive if we add some ingenuity. But there is an economic edge to the story, which is obvious when we look at, sorry, the pointer is here. When we look at the causes of death in the developing and developed world, it's very clear that infectious disease is prominent in the developing world, and this is reflected in the money allocated for research. Only the NIH for 2013 awarded more than $5 billion to research in cancer, and after that come cardiovascular disease, AIDS, diabetes, Alzheimer. Obviously, malaria is not there. To find figures for malaria research, we must go worldwide. And there it's worrying that not only the numbers are much more smaller, it's $2.5 billion only for malaria for the whole world. This was only in the US. And maybe the worst thing is that this is reaching a plateau. Then there are no perspectives of having more research for malaria in the near future. When I tried to find figures for nanoscience and malaria, I didn't find any. Then it occurred to me that the best way would be to look in the Web of Science, and there you can find only about 30 hits for nanomedicine and malaria. And then because 1/3 are from our group, it was fairly easy to estimate that the annual global budget worldwide for malaria, it cannot be much more than $200,000 US, which means that whatever we do, it has to be done at a low price, but this doesn't mean that it cannot work. It has to work as well as the best nanotechnology, but with a reasonable price. Then, of the 4 main pillars that we are using today to fight malaria, which is vector control, vaccines, diagnosis, and therapeutics, we are focused right now on drugs, on therapeutics. And as you well know, the main problem behind malaria therapeutics is the appearance of resistance. A few years or even months after the massive use of any drug, resistance appears. This cannot be avoided probably, which means that there is a pressing need for not only for new drugs, but possibly also for new ways to administer them, so that these new drugs that will appear in the future, they will not induce the evolution of resistance. And then, in our case, we are trying to approach this problem through the use of targeted drug delivery, using nanocarriers targeted to malaria-infected cells, where we load drugs and try to improve their efficacy. Our first prototype was a bit ambitious. This is the way we administer antimalarial drugs today. The drug is free in the plasma for any cell to take it, which means that we must usually deliver relatively high amounts of drug to to have sufficiently high concentrations in the cells infected by Plasmodium. And this brings the problem of side effects. You cannot go above a certain plateau because above there you have side effects in people. On the other hand, if you deliver too low amounts, this is what induces the appearance of resistance. And we must be able, in any attempt to use drugs against malaria, to deliver them in overall low amounts to reduce those side effects, but locally the amounts of the drug for the infected cells have to be as high as possible so that we kill the parasite quickly, and in this way we reduce the evolution of resistance. One way to do this is designing nanoparticles where the drug is enclosed, and then those nanoparticles must fulfill two essential steps. One is obviously targeting, if possible, only the infected cells, and secondly, injecting the drug content into that cell. As I mentioned, our first prototype was very ambitious because we designed strategies to not only to cross the plasma membrane of the red blood cell, but also the membrane of the vacuole inside which Plasmodium lives, and even the Plasmodium membrane if the target is some enzyme which is in some organelle of the parasite. This is obviously very complicated, and this would make a very, very expensive vector, which when we went to the pharma companies, they told us, forget it, bring us something which works, but which is as simple as possible. Then this original idea that we called Russian doll has been a little bit stored, put in storage. We still think it useful, as we have seen before in a future case of malaria eradication. The last vectors will be hyper-resistant, probably, and then we will need very good tools, very efficient tools that then maybe can be a little bit more expensive, but not for today. These first nanocarriers, as I mentioned, have to fulfill these two essential steps: recognition of the infected cells, but not of healthy red blood cells, and injection of the drug inside the cell. Our first prototype, it was a liposome, where we included the drug, and which was targeted by specific antibodies against proteins which are exposed only in Plasmodium-infected erythrocytes. In vitro, we had very good results. This is to show this result, a field in the confocal microscope with several dozen red blood cells, and there was only one which was infected, selected on purpose, this field. And as you can see, the nuclei tell us that this is the only Plasmodium-containing red blood cell. This is the targeting antibody. This is the quantum dot that we used instead of a drug to show targeting. And then the only infected cell is the only which is targeted by our nanocarriers, and it's the only also that gets the content. This was very efficient. In only 90 minutes, we had this 100% efficacy in both ways. We did not target any healthy red blood cell. And then we were very hopeful that we might be close to the sought-after magic bullet against malaria. As you can imagine, this was not so. When we did in vivo assays, this is not so nice. The IC50 of the encapsulated drugs could be significantly lower, but we did not cure the animals. Then if you don't cure the animals, even if you improve drug efficacy, this is good, as good as nothing. We were in the right path. And we concluded that we had a good first prototype, but many things had to be changed of the three elements of a nanocarrier, namely the encapsulating structure, the targeting molecule, and probably the drug itself. We know now that by modifying those three elements, we can maybe achieve a better targeting, better encapsulation efficacies. Probably we can think about new targets. We call this our Lego game, where we have this toy consisting of three different elements, and by exchanging these elements, and choosing better ones, our idea was to improve efficacy. Our first step towards improving efficacy was using not liposomes, but polymeric nanoparticles made of this type of polymers, which are called polyamidoamines. They gave nice homogeneous suspensions, both by atomic force microscopy and by cryo-electron microscopy. And the idea was to substitute the liposome by these nanoparticles. The surprise was that in our first controls, when we were adding the nanoparticles to a mixture of healthy and infected red blood cell, we already obtained a specific targeting without the need for using antibody. And this reduced the cost very much, which was indeed very good news. You can see here there are healthy red blood cells which do not get the nanoparticle. This is polyamidoamine nanoparticle without antibody, and the only infected red blood cell which incorporates the nanoparticle. When we loaded drugs into these polyamidoamine nanoparticles, for example, chloroquine and primaquine, we obtain a nice slow release along 24 hours, more or less, which is good, taking into account the time of the Plasmodium life cycle. In vitro assays were also positive. Chloroquine alone at 2 different concentrations. For instance, this is 0.8 milligrams per kilogram per day. And encapsulated chloroquine into different polyamidoamines improved very much the in vitro activity. And in vivo, here, the results were very good. Also, in this case, we could cure the animals at concentrations of this 0.8 milligrams per kilogram per day. Free chloroquine was unable to cure the animals, but our encapsulating nanoparticles did. Then we are very hopeful that we are now on the right track. And the economic part that I was mentioning was also good in these experiments. Whenever we design a new nanocarrier, we always try to see how we try to normalize in order to compare the different nanocarriers. And we take as an example how much does it cost to improve tenfold the efficacy of chloroquine, which is already a very good antimalarial drug. With the first, per liter of blood, sorry. Then with the first immunoliposome prototype, this was very high, more than 50 euros, forget it. Second liposome prototype using heparin instead of antibodies as targeting molecule, that brought down the cost to €1. And with these polyamidoamine nanoparticles, this is just 40 cents, which begins to be reasonable. We are trying new types of polymers, namely dendrimers, that reduce to 0.5 cents this improvement cost. But dendrimers work very well in vitro, but not so much in vivo. So for now, I would place my best hopes in polyamidoamines. When we were looking at polyamidoamines alone, without any drug, we already observed that they had a mild antimalarial activity, which was manifested when we were adding the polymer to Plasmodium cultures. And then we knew also that the polymers, as you have seen in the confocal images, were entering the cell. They did not just stick to the outside, but they entered the cell. And then we thought here we might have some type of Trojan horse, in the sense that something that to the cell looks innocuous enters, and in the end it helps to kill the cell. When we were looking more in detail what polyamidoamines are doing in the infected red blood cell, you had seen already before that, but now here more in detail, you can see that it binds to the free merozoite. It doesn't only sticks to the infected red blood cell, and when this cell contains Plasmodium inside, is able to penetrate the cell and somehow bind to the parasite. But here it was very clear, by using these free merozoites, as you can see they are not inside the red blood cell, that polyamidoamines bind to them. And then thinking that this might be the mechanism through which polyamidoamines work as antimalarials, we have confirmed that indeed when we pre-treat a Plasmodium culture with polyamidoamines without any drug, the consequence is that in a normal culture you have what we call ring stages at the start of the next cycle after the red blood cells have burst. But when you treat this stage or this stage with polyamidoamines that enter the cell and bind the parasite, the resulting parasites are unable to infect new red blood cells. Then we think we might be having here a double activity of these nanocarriers, first as carriers of drugs, but once they have finished their role as drug nanocarriers, they would have a second life by coating the free parasites and preventing somehow the invasion step. And finally, do I still have a couple of minutes? Finally, I will present our next goal in the near future, which is moving from red blood cells to transmission stages between human and mosquito, which there is a consensus in the malaria community that this is the place where we have to focus our efforts in order to achieve eradication. The good thing about mosquito stages is that unlike in humans, where in every infected human you can have up to 10 to the 11 infected red blood cells, in a single mosquito, some of the Plasmodium stages, you might have 2, 3, 4 cells only, in particular the oocyst. But then you will tell me, obviously, okay, you will have very few cells per mosquito, but you have trillions of mosquitoes, which is true. And then here is where the problem is. Then if we want to target mosquito stages, we will need probably two things. One is first new nanocarriers, different from the ones that we are using, and also new drugs that work through radically different mechanisms, because if we just change the target cell from having trillions of red blood cells inside a human to trillions of Plasmodium inside mosquitoes, if the drugs works in the same way, that we have to reach every single cell, this would not be optimal. Then we will have to think about new drugs. We have some idea in that direction, but because of patent reasons, I cannot talk about these new drugs. But I can talk a bit about our first efforts in targeting the mosquito. This is the last slide where we were exploring if our polyamidoamine nanoparticles could be used to deliver drugs to mosquitoes. We fed Anopheles atroparvus, which is our local Anopheles in Barcelona, with nanocarriers, polyamidoamine nanocarriers in the sugar mill. And we wanted to see in this preliminary experiment if the nanocarriers enter the mosquito and exit without any other effect, or if they would exit the stomach but into the mosquito body. And there, especially interesting are the salivary glands, where we know that are the sporozoites that are injected by the mosquito in the infected bite. And actually, the result was promising. This is 48 hours after feeding the mosquito with fluorescein-targeted polyamidoamines. As you can see, this is the thorax, and these are the salivary glands. We know that the fluorescence is there. We still have to nail down if this fluorescence is of the nanocarrier or of parts of the polymeric nanocarrier itself, or if fluorescein has been cleaved from the polymer, and this is just fluorescein fluorescence. We don't know that yet, but this is our next step, using polyamidoamines for a third antimalarial strategy, which would be delivering drugs to the mosquito. The final message that I would like to convey is that no matter if we talk of magic bullets, Russian dolls, Lego, Trojan horses, we believe that nanomedicine can be an option for medicines of developing countries, not only malaria, but probably other arthropod vector diseases. And finally, I want to acknowledge the students who did this work and our funding agencies, and thank you all for your attention.
Thank you. Thank you. Thank you, Dr. Fernandez, for talking about the future trends of malaria control. Any question or comments for Dr. Fernandez?
Yeah, I'd like to know, you mentioned that look like from your experiments, your polyamidal, the nanoparticle, can recognize only the PRBC. Do you know why? Because of the membrane of the RBC has some special, or because it's different?
Right.
Intact, not intact membrane.
The red blood cell infected by Plasmodium has very different properties from the normal red blood cell membrane. There are many different proteins out there, but our experiments, we simply did an affinity chromatography where we bound polyamidoamines to the column, and then we passed through there an extract of infected or healthy red blood cell extracts. And then just to see if some particular protein was sticking that we could identify as the receptor. Then what we see is that polyamidoamines are very sticky for some reason that we don't know yet to the infected red blood cell. And then this gives the polyamidoamine probably an edge because the infected red blood cell is very permeable to small nanoparticles of up to 70 nanometers. Then we think that the mechanism is rather unspecific in the sense that polyamidoamine nanoparticles, because of the polyamidoamine nature, they tend to stick preferentially to infected red blood cells. And if they stick there for a few seconds, probably, that allows the cell to internalize them. So
even without the drug, no chloroquine, only the particle, empty particle can recognize the PRBC.
Right.
So maybe we would like to know which molecule is interaction happened there.
Right. There seems not to be a unique interaction molecule. There seems to be not a single receptor. Because when we try to fish for this receptor, we obtain many proteins binding to the polyamidoamines.
But all from Plasmodium side, it's not a normal
also from
erythrocyte side.
Also from the red blood cell, in our controls where we were using non-infected red blood cells, we also had a significant number of proteins sticking there. Then it seems to be a rather sticky polymer. But if the cell, like the normal red blood cell, which doesn't have any interiorization mechanism, doesn't take it, then it doesn't harm the cell. But the Plasmodium infected red blood cell does apparently take it.
And another question is, I would like to know the metabolism pathway of this.